this video, we are going to discuss position, velocity, and acceleration. And specifically, we're going to talk about how these quantities, how we can do x versus t, position versus time, velocity versus time, and a versus t graphs. Okay, so we're going to talk about those things specifically. All right, so let's start with position, right? What is position? Well, position is just where you are, right? And that makes sense. And so position is I'm located at x equals 10 meters. Or you could say my position is given by 10 meters in the x, 3 meters in the y, and negative 4 meters in the z, right? In the z direction, all right? If you're in three-dimensional space. And so there are many different ways to describe position, but let's just stick with one dimension for a second here. So position versus time. And position versus time, I just want to point out, we always say these titles as y variable versus the x variable. Okay. What do I mean by that? Well, I mean you have a y-axis and you have an x-axis. This is your y-axis, is your vertical one, and your x-axis is horizontal. And so whenever you see these graphs, a lot of the time we label position by just the uppercase X, but because, and this is a common point of confusion, X is going on the y-axis, not on the x-axis, right? Because this X over here is referring to the X of position, right? X, Y, Z, position, whatever it is, that's referring to a position in units of meters. I'll use a different color there. So X is referring to that position in meters. X over here is just the x-axis, right? Or you could just call it the horizontal axis if you don't want to get confused. But this is a common point of confusion I see where people want to put X on this axis, right? Because they're thinking, oh, it's the x-axis, so the X for meters should go down there. Well, no, this X, again, is not the x-axis. This is talking about just your position, and position is something that's going to go on the y-axis, right? That's why we call this an x versus t graph. Okay, and so then we'll put time on the x-axis, right, on that horizontal axis. And so this doesn't have any negative values, right? I could extend the axis down here and out here. I'm not going to right now, and mostly that's because we don't have negative times in physics. You can, but generally we measure time from t equals 0, okay? You don't have to, but it's generally how we do it. Okay, so let's just say we have a straight line, all right? And so we can kind of figure out which time and which position those are. I'm just gonna call this x final, and I'm gonna call this t final. And then this one right here, I'm gonna call x0 and t0. Or you could call it, actually I'll say x initial and t initial, and that's just at 0, 0, right? If you want to write it as an ordered pair. Okay. So, what can we get from this graph? Well, one of the most important things that we can get from this graph is actually just the slope of the graph, right? What is the slope? And so it's important to define what a slope is, right? Just to make sure everyone's on the same page. So slope is equal to kind of your rise over run, is how I like to say it. Rise over run, or in other words, it's your vertical distance traveled divided by your horizontal distance traveled, right? And when I say distance, I just mean how far did you go on the graph, not necessarily something in meters or whatever, although in this case, it will be a distance for the vertical. Right, so we have vertical divided by horizontal, okay? And so what is the slope of this line? Well, let's just plug that in, okay? So how much do we rise by? Well, we need to figure out how much does this value change. So we go from 0 as our initial position, and we go to a final position of, and excuse me, I actually circled the wrong one. This is our y initial, right? We go from x initial to x final. So delta x is equal to x final minus x initial. That's something you just have to remember, right? Whenever you see delta, just a change in x. So delta x is x final minus x initial. Delta t is equal to t final minus t initial. So you just take whatever the final value was and subtract the initial value from it. Okay, but we already said x initial here and t initial for our cases are 0. And so for this particular case, because we know we're starting from 0, 0, we can say that the slope delta x divided by delta t is equal to x final over x initial, right? For this particular circumstance, this is really the formula over here that you really want to remember. So slope of an x versus t graph is equal to delta x over delta t is equal to x final minus x initial over t final minus t initial. Okay, so in our particular case, this is what the slope is. Okay, but what are the units of slope, right? Because it's actually really important that we remember units of slope. Well, our vertical units, all the way up here, are in meters, and our horizontal units are in seconds. And so the same rule applies. And so this is going to be in meters divided by seconds. Okay, now meters per second these are actually the units of velocity. Units of velocity. And so you can see that from an x versus t graph, if you take the slope, then you actually get the velocity during that time interval. And this would be an average velocity. Now, what if we took the slope just from here to here, and we had more values to plug in for x initial and x final for these? Then you would get the average velocity during just this interval right here, this smaller interval. Okay, so we took, in this example before, we took the average velocity over this whole interval, but what I'm saying is you can do this for any interval. All right, now I'm going to make one more comment, and this one may or may not make sense depending on the background that you have in calculus. Okay, so I am saying that you can keep taking smaller and smaller and smaller intervals until you get an infinitely small interval. And once you get an infinitely small interval, where these 2 points are so close they're practically touching, then you get an instantaneous slope. So you no longer have the average slope over an interval, but you have the instantaneous slope. This is related to the derivative in calculus, the derivative of a function. Okay, so I will leave it at that, and we will keep going from there. But just know that you can take the average slope over any interval, big or small, and you will get an average velocity for that interval. And you can make that interval smaller and smaller and smaller until you have an interval so small that the points are practically touching, right? That difference is pretty much 0. And when you get to that point that your interval is that small, you have an instantaneous slope, no longer an average slope. Okay, so let's talk about how to interpret these graphs. Okay, interpretation. Interpretation of x versus t graphs. Let's look at one like this. X in meters, position in meters, and we got time in seconds. And this is our graph. Okay, so let's say this is 1 second, 5 seconds, 10 seconds, and let's say that this is 7 meters. Okay, just some random numbers I'm throwing in. So how do we interpret this graph? Well, anytime you have a flat line, all it's saying is that the object is standing still. It's not moving. And so let's look at this at 1 second. At 1 second, we're at 7 meters. At 5 seconds, we're still at 7 meters. At 10 seconds, we are still at 7 meters, right? And so very clearly you can see that what does this mean? Object is not moving. Object, person, car, whatever it is, the object is not moving. Okay, let's look at another one. X meters, t seconds, and let's look at one with the slope downward. And this is very similar to the one up here where the slope is going upward. It's going to be essentially the same kind of motion. Okay, and so we have this straight but diagonal line. So up above we have a straight flat line. Now we have a straight diagonal line for this case. And let's just say that we take this to be 7 meters, 5 meters, 3 meters. And let's take this to be 1, 5, 10 seconds again. Okay, So we'll kind of move this down just a little bit. Okay, so at 1 second, it looks like we appear to be at 7 meters, right? And then at 5 seconds, it appears that we're at 5 meters. And then at 3 seconds, it appears that we're at 10 meters. Okay, and what this means is that you can see that the slope of this line, and I'll write m equals constant. Okay, why did I write m? Real quick, y equals mx plus b is the equation of a line. So in this case, x equals some slope times t plus b. Okay, because again, this is the y variable and the x variable. This is where there's confusion. Our y variable is x, our x variable is t. So our y variable is position, our x variable is time. Okay, so that's the equation of a line, and so I'm saying m is the slope, and that's constant. So m is constant. So what does it mean when the slope is constant? Well, the object is clearly moving, right? Because it was at this position of 7 meters, and then 5 meters, and then 10 meters. And so it's clearly moving, but, you know, I should actually make this 0 meters, just to be, and I know that usually we would put 0 over here, but it really doesn't actually matter, okay? Why am I doing that? I'm doing that because I'm going to take the slope of each of these points right here, okay? Each of these intervals. So I'm going to take that interval, and then I'm going to take the slope of this interval. Okay, and we're going to see what that slope is. So slope, m, is equal to the final, x final minus x initial. So x final was 5 meters. So rise over run. So 5 meters minus 7 meters. And I'm going to put the meters out on the side. 5 meters minus 7 meters. And the time was 5 seconds minus 0 seconds. Okay, so that is -2 meters per 5 seconds. Okay, and so that would be -2/5 meters per second. That's our slope. So we'll call that m1. m2 is going to be 3 meters minus 5 meters over 10 minus 5 seconds. Once again, -2/5 meters per second, and that's our answer there. So you can see we have a constant slope, and this is actually our velocity, right? Meters per second is velocity. So that's the interpretation of a straight diagonal line. Okay, now let's do a final example here for the x versus t. Now we have x in meters, we have t in seconds, and we are going to have a curved line. Okay. Now I'm going to do this one qualitatively instead of quantitatively. So in other words, we're just going to use pictures, no numbers, right? So let's do that. So let me get out a highlighter and look at the slope at this point right here, the instantaneous slope. And but for that, I'm just going to do a tangent line, right? And if you don't remember, a tangent line is, let's just say we have some sort of circular path or any sort of curved path. A tangent line is just if you take the point, it's at any point on that line, it's just the instantaneous slope at that point. And so you can kind of visually see what I'm talking about, right? You take any point, and that's the tangent line, right? And so it's not going to be this line right here. That's not a tangent line. That goes straight through the point. We want one that lays just on top of it, right? And I could be more mathematical, but that's as far as I want to go there right now. Okay, so if you look at this point down here, we have a tangent line that's basically flat. So we'll just say that that one is 0. And then you see that we start to get a slightly more positive slope. So I'm just going to represent that by a plus sign. And then right here, it's even more positive. And then right here, yet more positive. Okay, so what does this translate to? Well, it translates to something that is actually accelerating. Okay, and we'll come back to this in a little bit. But the idea here is that this object, this car, this person, whatever it is actually accelerating. So it starts from 0 meters per second, and then it has some positive slope, so it has just some positive velocity, but then the velocity is even more positive, right? Because the slope is more positive. And then it's even more positive than that when it gets up to here, right? And so the velocity is increasing. So anytime you have any sort of curvature in an x versus t graph, it's either accelerating negatively or accelerating positively, right? And I'm careful not to use the word decelerating because I don't like that. I don't think that's a good physics word. So in this case, it's accelerating positively, right? We're starting from 0 meters per second. We're getting more and more and more positive in our velocity. But let's just take an example then where we do this, right? So we start from a slope that is very positive, and then less positive, and then less positive, and then 0. So this would be acceleration in the negative direction, perhaps. Just depends on how you put your coordinate system, and we'll get more into that later. But for now, just anytime you see that sort of curvature in an x versus t graph, you know that there is acceleration involved in the motion. It's no longer constant velocity motion like we had up here, constant velocity, and these are keywords to remember. So this is constant velocity motion, and actually this also is constant velocity motion, right? Because it just happens that the constant velocity that it's moving at is 0 meters per second, right? So it's kind of the arbitrary, or I should say the, it's the obvious case, right? The obvious case where we're moving at 0 meters per second, in fact, not moving, but that still is considered constant velocity, right? And so this second one is constant velocity. This one in particular is constant acceleration, and you wouldn't necessarily know that right now, that it's constant. Why not non-constant acceleration versus constant acceleration? More of that will come. Okay, but for now, I'm just letting you know that this is constant acceleration. So let us go on to velocity versus time. Okay, and now that these concepts have been more introduced, should go a little bit faster. So v versus t, right? Because we take our y variable versus our x variable. So v versus t is how we're going to call that. And let's draw that. So v versus t. Okay. Now I'm going to draw, I'm actually going to give this one a negative axis. Okay. And this is super common actually. So I'm not just doing this for fun per se. It's actually, this is something super common. Okay, so velocity has units of meters per second, and time has units of seconds. So let's just start right away with the slope, the units of the slope. Okay, so for slope, we're going to have units are meters per second is your horizontal, or is your vertical units divided by your horizontal units. So in other words, meters per second squared. And these are units of acceleration. So, with the case of the x versus t graph, we had units of meters per second for our slope, right here, units of meters per second. So our slope of our x versus t graph gave us velocity. Well, when we go down to our v versus t graph, we still can get more information from the slope. In this case, the slope is going to give us the acceleration. And just as before, you can do that over the whole interval and get the average acceleration over the whole interval. You can do that over some small interval and get the average acceleration over some small interval. And once again, just as before, you can look at one single point, right, where there's really 2 points, but they're infinitely close to each other, right? The distance is so infinitesimally small that you get an instantaneous acceleration. Once again, for those with calculus or some knowledge of calculus, this is just the derivative of the velocity function at a point. It gives you the instantaneous velocity. It gives you the instantaneous acceleration. Okay. What can we interpret from these graphs? I'm going to go straight to the interpretation now. So, straight to the interpretation of these types of graphs. So, first one that you might see is just, again, a flat line. Okay. And so, specifically, let's say that we have a flat line on this axis right here. I should just draw the arrow that way. Okay. So we have v versus t. So v meters per second, t in seconds. Now let's say that we have a straight line right at 0 meters per second. What does this mean? Object is not moving, right? Because at any point of time, let's say we take t equals 1 second, t equals 5 seconds, t equals 10 seconds. At any point of time, the velocity is 0, right? V equals 0, V equals 0, V equals 0. So it has 0 speed, and it's not moving in any direction, right? And so we have 0 meters per second, the object is not moving, okay? Let's go to the next type of graph, and in this one, we're going to have it cross the x-axis, just like the one actually above, okay? So crossing the time axis. And I'm just going to do V and T. Okay. And if you were asked what happens right here, right at this point where it crosses, well, V equals 0 meters per second, right? Now the velocity up here is some positive velocity, and then right here it's some less positive velocity. Right here it's 0. And then we get a negative velocity and some even more negative velocity, right? But at this point, velocity is 0 meters per second. So the object is not moving. But furthermore, we can actually say that the object is turning around. Okay, and why would I say that? Notice how it goes from the positive half of the V versus T graph into the negative half of the V versus T graph. That transition from the positive side to the negative side tells you that the object is turning around. It has a positive velocity. Positive is what tells you the direction, right? With all vectors, you have a magnitude and direction. And so you're told that it's moving with some positive velocity, and then it's moving with some less positive velocity until finally it has a velocity of 0, and then it's moving in some negative velocity, and then some more negative velocity. And so this is like the equivalent of you're driving down the road in your car, and you hit the brakes, and you come all the way to a stop, and then right when you come to a stop, you flip the car in reverse, and you continue going backwards, right? And you go faster and faster backwards. That's what's going on here in this situation, if you want to give some sort of physical interpretation to that. Okay. Now let's talk about two more types, and we're just going to do them right next to each other. So V versus T, V versus T. And I'm going to do these kind of quick. So one with a negative slope and a positive slope. So for this one, acceleration is less than 0, right? Because the slope is negative. So acceleration is negative. Okay, so the slope is negative, right? It's going down. Over here, slope is positive, so that A, the acceleration, which is the slope, is going to be positive. Acceleration is positive. Okay. So those should be all the interpretations, the major interpretations there for that graph. There's more that we could say, but that's enough for now. Finally, let's go to acceleration versus time. Okay. So acceleration versus time, let's see, A, and meters per second squared, right? We figured that out above, all the way up here, right? Units of acceleration are in meters per second squared. Okay, so we figured that out. And then A versus T, so T in seconds. Okay, and let us just make a very simple graph, right? A flat line. Okay, now I could keep doing the same procedure as before, where I take the slope and I say, what are the units of slope, right? And well, meters per second squared divided by seconds. We're not going to do that anymore. This is as far as we need to go. There's more that you could get out of it, but not for an introductory physics class. In fact, even most advanced physics classes don't cover concepts like this. If you want to take the slope of acceleration versus time graph, you're probably in some sort of robotics or engineering field. It's just not useful in most other fields, okay? But you could keep taking the slope of one graph after the next after the next. We just don't need it for this type of physics that we're doing. Okay, so, and again, that's even most advanced physics topics. It's just not necessary. It's not that it's difficult or whatever, it's really just not necessary in most circumstances. So acceleration versus time. Once again, you got your y variable, which is your vertical, versus your x variable, right? Same thing. So time is always on that horizontal axis. Okay. There's really just 3 interpretations. So I'm actually going to just draw them all on the same graph, and you can understand that obviously you're not going to have all 3 of these at the same time. You would have different graphs for these, but let's just talk about the red one. So above x-axis and it's flat. Then the acceleration is positive. Okay. What about this one? Acceleration equals 0 meters per second squared, right? And you really should put units. I'm being a little bit careless with that one. And I'll write positive. Okay, and acceleration is 0 meters per second squared. And then finally, what about this one? Acceleration is less than 0 meters per second squared, so it's negative. Now, yeah, you could have diagonal lines and curved lines on acceleration versus time. Not really in a Physics 1 course, because that's more complicated motion. You actually will see that pretty much the only time in a Physics 1 course that you see any sort of curved line is on an x versus t. And then the most complicated thing you see on a v versus t is a diagonal line, and then generally the most complicated thing you see on an a versus t graph is a flat line. And there's a reason for that. It's actually related to the calculus. So anytime you have a curved line, that is at least an x squared variable. Okay, so if we're talking about y equals mx squared plus bx plus c, that would be kind of the equation of a line with a curve in it. All right. And then I mentioned the derivative, again, for anyone with calculus. Well, if you take the derivative, you get 2mx plus b. And again, if this doesn't make sense, that's okay. I'm just saying it for the, I'm trying to make a point here. And the point is that you see that this squared power diminishes as we take one derivative to the next. So we go from squared to the first power, and then x to the 0 power is just 1, right? And so that's just 1. Okay, and this is the reason that we usually get a curve on the x versus t graph, diagonal line on the v versus t graph, and then a flat line on the a versus t graph. Again, for Physics 1 applications. Okay, and so those are really the interpretations to remember for an a versus t graph. Now, sometimes you might see a jump in an a versus t graph. So you might be going and then it jumps down to somewhere else and then jumps back up. This is a theoretical jump. So you might see this on a physics exam. You're not going to see this sort of jump on a physics lab where it actually, the line disconnects, right? If you're in a physics lab and you're measuring the acceleration of something, it might be really fast, but the line will always be connected. So just so you keep that in mind, jumps in the graph are theoretical only. They're not actually physically observed, right? You can have jumps. They're just going to be connected jumps, right? You're not going to have a dotted line where it actually just picks back up somewhere else, right? And so let's just do one final example here to just kind of tie everything together. And this is to show, so example, this is to show the relation between all the graphs. Now for this example, we're going to have this curved parabolic function. So parabolic means we have an x squared variable. So in this case, that would be a t squared. When I say x squared, again, I'm being a little careless. When I say x squared, I'm talking about that function, y equals mx squared plus bx plus c, right? Or I should say ax squared, really. That doesn't really matter. A, b, and c are just constants. Okay, so this would be instead x equals a t squared plus bt plus c. For our purposes, that's what we're talking about. Okay, something like that, some function like that. So let's do the same game, except this time we're going to draw the v versus t and the a versus t graphs all together, one right on top of the other. And this is a super helpful method to go from one graph to the next to figure out which graph, what your graphs look like. So if you're given an x versus t graph, let's just take the slope at kind of consistent intervals here. So slope is 0 there. We don't have any numbers, so we're going to write positive, positive, and then, you know, so positive, more positive, most positive. Okay. Well, from here, and actually, you know what? I am sorry. I'm going to redo this because I want to showcase even more information. Okay. So here we can agree that this is the most negative point, and then the slope becomes even less negative, and then 0, positive, more positive, most positive. So that's that graph. And then you want to go to the V versus T graph, and you say, well, where do I even start? Well, we said the V versus T graph, that corresponds to just the slopes. Okay, and so what's the maximum slope we have? It's that triple positive. Okay, and then we had a double positive, and then we had a single positive, and then we had a 0. We also had a negative, a double negative, and a triple negative. Okay, and these were all at equal intervals from each other. You know, this is 1 second, 2 seconds, 3 seconds, 4, 5, 6, 7, whatever. They're equal intervals from each other. I don't know that for sure, but I'm just telling you that's about what they are, mostly because obviously I know the correct answer to this sort of problem, so it's just something that comes with some experience as well. Okay, and then we can say, well, we go from negative, triple negative to triple positive. Let's just draw a diagonal line. Okay, and so what you can see is, like I said, anytime that we go from the negative side of the V versus T graph to the positive side, or vice versa, if we were to go from the positive to the negative side, anytime we do that, the object is actually turning around. Okay, so object turns around here. Okay, so that gives us some information about what's physically going on here. Okay, and so what else can we say? Well, what's the slope of this graph? Well, you can see the slope is constant no matter what point you pick. The slope is just some positive slope, right? We don't know if it's a positive, double positive, triple positive. It doesn't really matter because it's not in relation to anything else. It's just positive. Okay. From there, we can go ahead and just draw a flat line on our A versus T graph. All right, and that has a slope of 0. It doesn't really matter because, like I said, we don't really care about the slope of an A versus T graph. And so what can you tell about this? Well, from this curve up the top, we figured out that the velocity versus time is a diagonal line. The acceleration versus time is a flat line, right? And so the velocity is changing as time increases. So it's not constant velocity motion. What can we say? It is constant acceleration motion. Okay, so constant acceleration. That's what we can say about this object. So on an X versus T graph, whenever you see this sort of parabola, right, and not just any sort of curve, right, because what if it did something weird, I don't know, something later. It's anytime you see an actual parabola and you know that that is some x equals at squared plus bt plus c function, right? Anytime that you see that, you know that this is constant acceleration motion, right? Because I didn't plug in any numbers. I just analyzed this qualitatively, and it was discovered that this is constant acceleration motion just by taking the slope of one graph to the next. Okay, and so that example really just concludes this look at position, velocity, and acceleration versus time graphs.